I'm going to do example 2 and example 3 out of section 6.4. So example 2 is the elevator problem. So basically, we're looking at an elevator that has a load capacity 4,000 pounds, or say 27 people. Well, if you look at this, if you take the 4,000 pounds and divide it by the 27, you get 148 pounds per person. That's the number that the capacity of the elevator is based on. Well, we're going to look at a worst case scenario. What if it's all males? You know, bigger than females, right? Now, we know that with males, in previous problems, if you read, the mean weight of the male population is 180 pounds with a standard deviation of 39 pounds. Now the first thing we're going to do is just a problem just like we were doing in 6.2, where we're going to look at an individual. So randomly selected male. Okay, so we're looking at X because it's one individual. And we're going to ask ourselves, what's the probability that a single male would weigh more than 148 pounds? So I'm going to draw my diagram to do the analysis. See, I think I got everything I need here. I've got those in my notes. So I draw my normal curve, I put my mean in the middle, I put my standard deviation right under it, and then I go, okay, where does 148 fall? That's over here. I go back, I'm looking for a probability greater than 148. I want this area. And just by looking at my diagram, I know that the probability looks rather high. So if I get a small number, I did something wrong. Okay, so I need my z-score. Once I got the z-score, I go to the tables and get the area. Z is my x value, that's the 148. Subtract 189 over 39. Quick check I do, I look at the numerator. That's negative. That makes sense because I'm to the left of the mean, so I know z is going to be negative. Negative 1.05. Now, you could look in the table and get the area to the left, because that's what the table gives you, is this area to the left. And you could then take 1 and subtract that area and get the answer, because that's a complement. You're looking to the stuff to the right. I'm going to use symmetry instead. If my z-score is negative 1.05, I'm going out to 1.05, and I'm looking for the area to the left of that. These areas are the same. I do that because if I look in the table, I get the area to the left, and I don't have to do a subtraction. 0.8534. So the probability that a randomly selected male would weigh more than 148 pounds, given that's the mean and standard deviation of our population, is about 0.85. That makes sense because I knew it was rather high. Okay, part B here is we're going to use the central limit theorem, because we're going to ask ourselves, suppose the door opens on the elevator and there's 27 males in there. What's the probability the mean weight of 27 males is greater than 148 pounds? This is key because now we're not using individuals. Now we're using a sample because we're looking at the mean and not just the weight of a single person. So this is central limit theorem. And there's my sample size. So n equals 27. Now, the criteria of the central limit theorem, if n is greater than 30, we don't have to worry about it. Here, n is less than 30, but if you think of the distribution of weights of males in a population, we're going to assume it's normally distributed. That's the other criteria, so we're okay. Okay, so how does this change my problem? Basically, everything is the same except the standard deviation becomes smaller. It tightens up my normal distribution. So I do the analysis the exact same way. But now, there's the mean of the sample distribution. Notice I put this little X bar subscript, but central limit theorem says that's the same as the mean of the population. Now I want the standard deviation of my sample. Central limit theorem says, oh, that's the population standard deviation divided by the square root of n. So when I go over here, my mean is still 189. But my standard deviation is now 39 divided by square root of n. And n is 27. Same picture, 148. Looking for the area to the right. The only thing that changes now is now my z is x bar subtract mu over sigma over square root of n. I don't need that little x bar because I'm going to use this. So now I'm talking about mean weight of 148. Subtract 189, sigma 39 over square root of 27. So, in this case, z is negative 5.46. That's a huge z-score. That's over 5 standard deviations away. That means the area to the right here is basically, for all intents and purposes, 1. So it's a huge probability that those 27 guys have a mean weight greater than 148. So that means, remember 27 times 148 is 4,000 pounds. Well, if the mean weight is more than 148, we're bigger than this, you just say not getting on. So that's a central limit theorem. And now I'm going to do example 2, or 3, I'm sorry, with the temperature, because it's the other example the author does in this book. And we're going to look at temperature. And we're also preparing ourselves for Chapter 7 and Chapter 8 when we're testing claims. I don't know if you're like me, but when I grew up, I was told that the mean temperature of humans is 98.6. Anything above that is a fever, and anything below was hypothermic. So, this is our claim. Now, researchers at Maryland randomly selected 106 individuals, and they found a mean temperature of 98.2 degrees. What we're going to do is this significant compared to that? So we're going to ask ourselves, given this, along with standard deviation of 0.62, that's rather important, what's the probability that a sample of 106 people would have a temperature of 98.2 or less? We always need that greater than or less than so that we get an area. So asking ourselves, what's the probability that X bar is less than 98.2 given this stuff? (98.6). Okay. Sigma now is 0.62 divided by square root of 106. Because central limit there, and we're working with a sample. 98.2 is right here. I want the area to the left. I've done my analysis. Now I'm going to find the z-score, and I'm going to come back and see if it gives me any evidence against this claim. Okay, my z, 98.2, subtract 98.6, divided by 0.62, divided by the square root of 106. Negative 6.64. Okay, that is way out here in the left tail. Now, if this is the 98.6, the probability that we're at 98.2 or less is basically zero. There's really no area to the left of that. So this probability is, for all intents and purposes, zero. So what we're going to do is, now we've got some evidence. We have evidence to reject this claim. And that's what we're going to do starting in Chapter 7, where we're failed to reject or we reject the claim. We never prove anything. This is statistics. We're just getting evidence. So essentially, here's what happened. We had a claim. This is what I grew up on. Yeah, your normal temperature is 98.6. There's a research project. Oh, we're getting a mean of 98.2. What this is saying is the probability that you go and select 106 random people and you get a mean of this is so low if this is true, because it's so far away from here, 6 standard deviations, that wait a minute, I don't think this is from this population. I don't think this is true. So I reject it.